does the Milky Way look like? Is it more like this artistic picture of this one? We don't really know. We know that the Milky Way have some remarkable structures like the galactic bar, spiral arms, but we don't know exactly their characteristics. And we can ask what are the processes that link the interstellar medium to stellar formation. And so to try to answer this question, we can use 3D extinction maps, which are maps that shows us the dust distribution in the Milky Way. So there is, for instance, this map from Vergely et al. That have a good resolution, but that extend only to 5 kiloparsecs from around the sun. So it limits our view of the Milky Way. And there is a more recent work by Roisey et al. That extend very far, even a bit more further than the galactic center. But the resolution here of the map not seems to allow us to detect real structures. But there is a paper in preparation by Marshall et al., where they managed to make a map that extend to very high distances, up to 14 kiloparsecs, and on which we can observe both large-scale structures and smaller structures. However, this map and the method they used, well, they use only 2 mass data, and the short distances are not well constrained. And so the goal of the method I will present you is to improve this map and to constrain even more short distances. So first, a little word about interstellar extinction. So interstellar extinction is a phenomenon that affects stars. So when we look at the stars, light will cross a cloud dust, and so the short wavelength will be scattered, which makes the stars appear redder, and the light will also be absorbed, and so the star will appear with a lower luminosity. And so on the color histograms, you can see the effect of extinction. For instance, in red, you have the color histograms for synthetic stars, okay? And in blue, for real stars with the extinction. And you can see the effect of extinction on this histogram. Okay, so now how to measure interstellar extinction. So the idea comes from the work of Marshall et al., 2006, and is the following. You have on one side observation, which consists of a catalog of real stars. And on the other side, we have a simulation, so a catalog of synthetic stars. For observation, we have the stars and the extinction that we cannot extract. And for the simulation, we only have stars. And so we assume that the difference between the observation and the simulation is solely due to extinction. And so we can try to extract a catalog of stars for given websites and find which extinction profile, so extinction as a function of distance, that will tell us where we have a structure, where we have dust along this line of sight. So for the simulation, we used the Besançon Galaxy Model. This is a stellar population synthesis model that takes into, well, as input some parameters, and that can give us for multiple line of sight in the galaxy a catalog of stars for which we have a lot of characteristics, the photometry distances, and many characteristics of stars. And then with this tool, we can study the structure of the Milky Way, and by comparing it with real observation. So we can, for instance, compare the catalog from the model to a catalog of real stars and try to find to have a 3D extinction map. For the observation, we used Gaia and 2MASS. So Gaia, why? Because we have estimation of distances, which allow to have a good estimation of the distance of the structure of stars close to us. But the problem with Gaia is that it's observed in the visible range, and so in the visible range, the extinction effect is quite strong. And so when you select select the stars according to, well, which have a good estimation of the value, you are only limited to stars that are quite close to the sun. And so we use 2MASS because 2MASS is in the infrared domain, and so it's much less affected by extinction, and so we can expect to probe to larger distance in the Milky Way. With our method, we do not want to do a cross-match between Gaia and 2MASS, because doing a cross-match can limit, in fact, our sample to a distance range which will correspond to the limit of Gaia. We just want to use all the information for both Gaia and 2MASS to have the maximum information available. So on one side, we have observation. On the other side, we have a model. We compare them using color histograms, and what we want is to find which extinction profile which apply to the BGM allows us to have the color distribution of both observation and model to be close to be very similar. So to find this extinction profile, Marshall et al. First implement a custom MCMC in Fortran that use only one worker and only 2MASS data. For us, we want to add Gaia data and maybe a lot of other surveys, and we want to use a more robust implementation of an MCMC, and so we switch to Python and use the MC package. And so with that, we have n parameters that are differential extinction that are arranged onto a regular distance grid, which gives us at the end an extinction profile. We can use multiple workers so that we do not find a solution that corresponds to a local maximum. And we assume an extinction law following the work from Fitzpatrick et al. 2019, using a constant RV value of 3.1, which is the mean value in the Milky Way. So for the result, we first look at a single line of sight through VLAC. So here you can see three extinction profiles. So extinction as a function of distances. Here obtained using only Gaia data, only 2MASS data, and 2MASS plus Gaia. So VLAC, it's located at around 970 parsecs. And what you can see is that we retrieve quite well the position of VLAC, and even more, we can see that the short distances are mostly constrained by Gaia, and large distances are mostly constrained by 2MASS. So the use of both Gaia and 2MASS without cross-match seems to be effective with our method to retrieve the position of clouds. So now, how to have a 3D map? Well, we just do multiple line of sight, concurrent line of sight, and we have at the end a 3D extinction map. So we try to map the region where we can observe the tangency of the Carina arms. So you have here three extinction map, polar view of the Carina arm regions. And as you can see, first, for this map, we observe the similar structure which corresponds to the Vela complex in both maps, as well as others. And the striking thing is that compared to the work of Marshall et al., it seems that we better constrained this structure at short distances. However, we have some differences. For instance, this region here that we do not detect in our map. So that's the differences. The map from Vergely et al. That have a very good resolution is only limited to 5 kiloparsecs. But our method can push to further distance. So these are the results up to 15 kiloparsecs. And here you can observe first that we retrieve structures that correspond to the tangency of the Carina arms. It matched quite well with some tracers like H2 regions, giant molecular clouds. So those are the red and blue points. And but there are some differences between our work and other works, like this clump of H2 region and giant molecular cloud, where we should expect to observe something in our map, but we do not. But well, in the work of Marshall et al. And Cornu, they seems to have something. So there are some differences, but one of the important result we have is that we have very good constraint on short distance, and we can see large-scale structure like the Carina arm. Then we can compare our integrated extinction map here with the Planck dust opacity map here that has been converted here into extinction for the sake of comparison. And what you can see is that the structure that we can identify with our map are very similar to what we can observe in the Planck dust opacity map. However, if you look at the difference more closely, you can see that we have some overestimation in the case of our method compared to Planck. And this can be explained with two reasons. First, the gradient of temperatures inside the clouds can make Planck underestimate the dust opacity and so the extinction. And we used a constant RV value for our work. And this can lead the method to overestimate the extinction. So those two effects go in the same way. And when considering them, we can see that the structure that we identify with our method are comparable to what we can identify in the Planck dust opacity map. So to conclude, with our method, we do not need to do a cross-match between our different surveys. We can cover large distances with our map while having very good constraints on short distances. There are some improvements that are still under study, like considering the fractal structure of the interstellar medium, or considering the subpixel gradient of dust density for each line of sight. And there are some perspectives for our work. For now, we only map a small region of the galactic plane, but we plan to map the entire galactic plane. Because we are using a model, we want to try to characterize the dependencies of the method on this model. And then, because our method allows it, try to use Spitzer data to probe at larger distances in central regions. And then there are some improvements that are possible using nested sampling instead of MCMC that could give us more robust results. Try to hybridize our method with other map to improve the constraint on maybe small distances and add constraint using gas observations. So well, that's it for me. Thank you for attention.